geometry of networks. Unfortunately, Ernesto could not make here in person, so this keynote talk is going to be remote. But we have here good equipment, so we can see everything. So we are orange, and please welcome Ernesto, and the floor is yours. Thank you.
Thank you very much. So thank you for coming, and also the organizer for inviting me to be in this meeting. I was very much hoping to be there, but I was returning from Munich because I didn't have the ETA to travel to Canada. So it was a big adventure, but at the end of the day, I had to return to Palma. So next time I will have the ETA in place, and I will be there with you. So let me start this talk by one particular, let's say, experiment or very simple experiment. So we have this simple graph here, and then I am marked here in two colors, two different paths that I will call P1 and P2. So it's very easy to realize that P1 is the shortest path in this particular, for this particular pair of nodes, P and Q. And P2 is a relatively longer path connecting the same pair of vertices. So in this experiment, which is a numerical kind of experiment, I will simply compute the so-called heating time, which is the time in terms of the number of steps that a random walker, which is departing from the node P, takes to hit by the first time the node Q, or the other way around because the graph is undirected. And we have invented this other concept here, which is the excess time, which is the time, again, in number of steps that take by the random walker, which is departing from P and arriving to Q, relative to the ballistic motion of this random walk. So by ballistic motion, I means that the random walker is directed from one node to the next just by taking only the edges of the corresponding path in a consecutive way. So we do computational experiments by taking several random walkers at the node P and measuring the heating time and the excess time at the node Q. So the results are here. So what we have is basically that the heating time going through the longer path is smaller than the heating time by taking the shortest path. And the excess time is even more dramatic because it's almost double through the shortest path than by the longer path P2. Of course, what happens here, you can immediately figure out. So we are not taking a random walker that is directed by this shortest path, but is moving in a diffusive way around this particular network. So we can understand, and this is from a paper by Gogni et al., which is mainly related to problems in brain navigability, that we can have two different kinds of navigability in a network. One of them is the routing or navigation process, which implies that we have a complete knowledge of the whole topology of the network, and we submit the particles from one node to a specific another node by taking certain kind of route in the network. The other way is to consider that we don't know the global structure of the network, and then we send this information in a completely random way, so by taking into account a diffusive process. So in this particular scenario, of course, the particle can go by any of the different routes, and we can understand here by route, let's say a walk in graph theoretic terms. I will go to the formal definitions later, but it can go even back and forth several times through the different edges and nodes in the graph. Although this seems to be very intuitive, you can find statements or affirmations like this in the application literature. For instance, it is impossible that one neuron among the trillions of neurons that we have in the brain, knows the whole structure of the brain. So it is almost impossible that the communication in the brain take place by the shortest path. So this immediately implies either the whole knowledge from every neuron of the global structure of the system, or the presence of a central controller, which is also controversial. But you can find in the literature in different areas affirmation like the shortest path plays an important role in the information transmission of a brain network. And it is very important measure to describe the internal structure of the brain. The shortest path can transmit the information more quickly and reduce brain consumption. So if we go back to the example that I have been showing there, if this were a brain, you can see that this is in a diffusive process. This is not true. And there are experimental confirmation that even aggravate a little bit more this statement. For instance, in this paper of 2013, Tomasi and collaborators has found experimentally that the most connected regions in the brain are the ones that consume more glucose in the communication between different regions in the brain. So if you have a region which is very well connected, of course, there could be many shortest paths going through this particular node. So navigation through shortest path is more energetic than navigation through other regions of the brain which are not so well connected. And of course, in this particular scenario, you are moving not through the shortest path. So the concept of shortest path is implicit in the most popular and well-known models for the analysis of the evolution of networks, such as the Watt and Strogat small world network model, published in Nature in 1998. So one of the most cited papers of all times in the whole story of the whole history of science. And the other one is the Barabachi and Albert model. So I will very sketchy mention what the models are about. In the case of the Watt-Strogat model, you start from a circular graph. So basically you have a regular graph with certain structure in which every node has a given degree by connecting it to the nearest neighbors and to the second nearest neighbor if you place like in here a round circle. Then the process start by removing some of the existing edges and rewiring randomly and independently these edges through the network, such that you will see that there are certain properties related to the shortest path that emerge immediately after this rewiring starts. In the case of the Barabasi and Albert model, what you have is a preferential attachment kind of model. So you start from a seed of randomly connected, a la Erdos-Renyi type of seed, and then you add new nodes which are connected preferentially to the nodes which are having the highest degree in this seed. So it is a mechanism in which the richer in terms of degree get richer in every step of the process. And again, you will see that this is very much related to the shortest path. So here are the basic results of the 4 pages paper of Watt and Strogat. So here you have the rewiring probability. This is in a log scale. And here you have a normalized pair of properties. So basically one of the properties try to measure the transitivity of the relations, but the most important for our case is the average shortest path length. So the average of the shortest path or topological distance in the network. And what Watt and Strogat observe is that when you do very few rewiring, so the probability of rewiring is relatively small, then the average shortest path drops very dramatically, but the transitivity of the network is still relatively high. So you have a regime here, not well defined in terms of the model, in which you have high transitivity and relatively small average path length. So this has certain similarities to, for instance, social networks. So we have a relatively small distance, and we use it to say that the world is small. This is a small world, but we have a large transitivity because if you have two friends, there is a high probability that these two friends becomes friends, and then you close a triangle of transitive relations at the end of the day. So the model based practically everything on the optimization of the shortest path length of the given network. The second model is basically trying to reproduce the observation that there are networks in which the degree distribution is not Poissonian, but is very fat-tailed. In particular, in this case, is power law. So you have networks in which there are a huge number of low degree nodes and very, very few nodes of very high degree, which are known as hubs. But the mechanism doesn't make any distinction between these, for instance, three scenarios. So you can have one central node in a star graph, and you can have the same node in a wheel, or the same node in terms of the degree in a complete graph. The three nodes are treated the same way. They are saying that they are central nodes in the three networks, because simply from this node you can reach exactly the same number of other nodes by using the shortest path. But if you do calculations about more diffusive kind of processes, you can see immediately, for instance, the propagation of a disease in these three different networks, that the rate of propagation or the rate of diffusion and the time at which the steady state is reached is different from these three scenarios. So I will briefly introduce some of the concepts. At this time of the conference, you possibly have seen this many times, so I will go very quickly. So I will use simple, undirected, and connected graphs. In the case that your graph or your network is not connected, simply treat it as separate graphs, because there are no communication whatsoever between the different chunks of the network. So I will use extensively the concept of walk, and in the physics literature, there is a confusion between walk and path. So in the walk, we have a sequence of not necessarily different vertices and edges in such a way that the particle can even do backtracking between the different vertices and edges. And what happens here is that the path is a particular type of walk in which there is no this kind of repetition, neither of edges nor of vertices. And we call a closed walk if the initial and ending vertices are exactly the same. See that you can have even closed walks in trees. So there is no necessity of having one particular cycle here. And it's a very well-known result in algebraic graph theory that the number of walks of length L, and the length of the walk is just the number of edges in this particular sequence of edges and vertices, between any two vertices, V and W in the network, is equal to the VW entry of the Lth power of the adjacent symmetry. So you can count walks by using powers of the adjacent symmetry. And this is a very sophisticated and useful tool for implementing algebraic techniques for studying walks in networks. So a few years ago, I introduced, together with my collaborator, Naomichi Hatano, the concept of a communicability function. So here the idea is that two vertices, two nodes in the network are well communicated if there are many walks that goes from one node to the other, independently of whether one of them could be the shortest path, because we give more weight to the shorter than to the longer walks. So then it means that the shortest path will always receive the highest importance in this series. But it has the advantages of you can express this measure of communicability between two nodes P and Q here in terms of the different powers of the adjacent symmetric, and we need a penalization in terms of the length of these walks in order to give more importance, more weight to the shorter than to the longer walks. So this parameter here has some importance in physical context, but immediately I will put it equal to 1 because it doesn't matter for the talk of today. But if we select that this weighting scheme is just the reciprocal of the factorial of the length, then of course this communicability function converge to the PQ entry of the exponential of the adjacent symmetric. There are other ways of weighting these, and all of them, well, not all of them, but many of them has been analyzed in the literature. So now we have two values for this expression of the communicability. I can consider the communicability of a node to itself is like the echo that a node has when it sends some information, how much of this information returned to this particular node. And then this is given by the total number of close walks that start and ends in this particular node. So we can think about that this is how much information is retained by an particular node. So if I send information, I send a letter, and the letter always returns to me and is not delivered, is not ended in the destination, let's say the node W, so I am highly, so the information is highly trapped into this particular node. But then we have also the communicability between the corresponding pair of nodes, which give you the facility that a node V has to send this information to another node W, or say in other ways, the facility or the attraction that the node W has for the information which is in the node V. So for having communication between two nodes, we have a certain competition between the possibility that the information get trapped in the origin or that the information goes to the destination. So we can then consider that this difference between information retained and information transmitted is a sort of resistance that the global network is putting to the transmission of information between one node V and another node W. So immediately I will prove analytically that this use of the word resistance is well justified here. But what I want first is that you capture the intuition. So this first term here is the capacity of a node to retain the information at it, and this is the capacity of the node to transmit the information to another node. So then if this term here is relatively small, then what we have is that there is a good transmission of information because much of them is transmitted and not retained in the original node. So here I will put hereafter this zeta equal to 1 for the sake of simplicity. But now we have that, of course, our network is undirected, so the same information which is transmitted from V to W is at the same time reciprocated by W to V. So we can take the sum of these two terms, of these two resistive terms. And the good news is that this sum here, which is not other thing that the difference between the amount of information retained at both nodes minus the information which is transmitted between the two nodes, is Euclidean distance between the corresponding nodes. So then it means that this quantity is a proper metric in Euclidean space in which the network is embedded. The proof is relatively simple. You simply write down this function in terms of the rows of the matrix of eigenvectors of the adjacent symmetric and the exponential of the diagonal metric of the eigenvalues of the adjacent symmetric. So see here that these are not the proper eigenvectors. So they are the columns of the transpose of the eigenvectors. So they correspond to a node and contain information about all the eigenvectors. So then because the exponential of any matrix is positive defined, so we can obtain always the square root of this matrix such that we can split the exponential of the eigenvalues in two terms, like in here, obtaining this expression that immediately becomes clear, that is Euclidean norm, particularly if we define that this term, which is here, is just the position vector of the node V into this Euclidean space that I will show you immediately what it is. And here you have that it is the square of the Euclidean distance between the corresponding nodes. So we have proof that this Euclidean distance induce an embedding of the network into an n-dimensional sphere. So then it means that the nodes of any network with n nodes could be embedded into the surface of one n-dimensional sphere, such that, as we will see here, if we take for the three-dimensional space, I cannot show you for higher dimensions here, but if we take here the three orthonormalized eigenvector of the adjacency metric of a graph having only three vertices, what we will see is that the position vectors doesn't correspond to these eigenvectors. So remember that they contain information on all the eigenvectors and eigenvalues of the corresponding adjacency metric. But then these position vectors give you the place in which these three nodes are collocated on the surface of one particular sphere, such that the communicability distance is just the chord between the two corresponding nodes in this sphere. So you can think that the geodesic through the surface is other type of distance, and you are right. But when the network is relatively large, this is practically the same as the chord because of the curvature of these hyperspheres. So in matrix theory, linear algebra, we have a concept which is an Euclidean distance matrix, which is called the EDM. And we call an EDM, and sometimes this produces some confusion, if we have a matrix such that the entries of this matrix corresponds to the square of Euclidean norm in a given Euclidean space. So then if these points furthermore lie on a hypersphere, we call this EDM an spherical EDM or Circum-Euclidean matrix. So we have that the matrix of the communicability distances that we have previously defined is a Circum-Euclidean distance matrix. Of course, you can define many other things like the angle between the position vectors and in this Euclidean space that we have called the communicability angles in the network, and you can work in for similarity properties of networks and so forth with it. So the first result I will show you here is that this Circum-Euclidean matrix is non-singular, and that we can write down the inverse of this matrix in this way, which we'll use immediately for one important result in this work. So basically what we are doing here is using the Sherman-Morrison-Goodbury formula, and then also proving that this denominator here is never equal to 0. And in addition, you can also, following the works of Gower in 1960s, that the sum of all the entries of this inverse is different from 0, which is required for a matrix being Circum-Euclidean, because this is related to the radius of the hypersphere in which the network is embedded. So now let's go to define this matrix here, which is given by the exponential of the negative of the adjacency metric minus, remember that a here is just the exponential of minus a multiplied by 1, so it's a vector. This vector transpose, and remember that d here is just a number, which is the total sum of entries of the exponential of minus a. And now we prove that this matrix that we have defined here is the unique Laplacian matrix, which is associated with the Circum-Euclidean distance matrix of communicability in the graph. So again, here the idea of the proof is based on a result by Balaji and Bapat, published in this paper in Linear Algebra and its application, in which they relate the Circum-Euclidean matrices with Laplacians, and then we can prove that the inverse of the communicability distance metric is related to this Laplacian in this way. then we find this term in the numerator here. We have already the denominator, and in this way, we have proved the result. So now we have the following important result. So if we have that this L is the Laplacian matrix associated with the communicability distance matrix, we can write down this communicability distance matrix in terms of the pseudo-inverse, more specifically, in terms of the Moore-Penrose pseudo-inverse of this Laplacian, in this way, in which the pseudo-inverse can be obtained analytically in this way, and this term here is just the diagonal of the pseudo-inverse of this Laplacian. You immediately will recognize this formula here. So this is exactly the same formula as what we use to define the resistance distance in an electrical network, in which we have placed unit resistance at every edge of the network. So it is then immediately the case that with this result, we are proving that the communicability distance matrix is indeed a resistive distance between pairs of nodes, and it justifies completely the name that we intuitively have given. So how to prove this? Well, basically, we use the idea of expressing the pseudo-inverse of the Laplacian in this term, which is true for any pseudo-inverse. And then we write down this expression of the first term by using the definition of the Laplacian in this way. And then because we have here the product of these two vectors and here again, and one matrix here, and we have to obtain the inverse of all of these, we again apply the Sherman-Morrison-Goodbury formula, and then we obtain this expression in here, in which we have this term f and g, now expressed in terms of the exponential of the adjacency metric, not of the negative of the exponential. Then we can obtain now this term here written in this more extended way, and we finally obtain the expression for the whole term that it is in this expression, which is just this term over here. And now we need only to prove that this matrix M is equal to this expression here. For this, we define this term that was defined by Benzi and Klinko in 2013, and is called the total communicability of a given node. And then you simply write down this expression in this way, and you finally prove the result. So this last part is mainly just to use substitution and algebraic work in order to see that the sum of these entries of the pseudo-inverse of the Laplacian minus the corresponding ij entry of the same give you the ij entry of the communicability distance matrix. So for those that don't know what exactly is the effective resistance in the algebraic graph theory literature, it is called the effective resistance between two nodes of a graph with a given Laplacian to this expression here, where this is just the basis vector corresponding for the node I and for the node j. This is again the pseudo-inverse, Moore-Penrose pseudo-inverse of the Laplacian. And this can be written for the case of the matrix in terms of this value of R, which is the diagonal of the pseudo-inverse, and the pseudo-inverse of the Laplacian. So then the square root of these entries of the effective resistance is also a metric, and this is a proper Euclidean distance, and you can also prove that it is even Circum-Euclidean. So then this allows us to say that the communicability distance matrix is indeed a resistance distance matrix between a pair of nodes. So this is what we are remarking here, and by extension, you can say that if this matrix here is any non-singular Circum-Euclidean distance matrix, then it corresponds to the resistant Euclidean distance matrix of a graph with the edges appropriately weighted. Here, the weights can be positive or negative, and you can figure out that there are attractions and repulsions between the nodes, but this is not important for what I am going to present here. So far, so good. What we have now is one particular metric that corresponds to the capacity of communication between a pair of nodes. So maybe it is mathematically elegant, but completely useless. So let's try to see if these give you information about networks, which is not provided by other measures. Before that, we have the following problem that take place in particularly any network problem. So for a given graph, you can have this Euclidean distance between every pair of vertices. So if this is my network here, and here is the node R, and this is the node S, I will have this distance, communicability distance here between the corresponding vertices. If this is short, it is telling me that in the embedding in the sphere, they are relatively close. But I am not an eagle in the network. I cannot fly from one node to the other. What I have to do is like a walker. So I go down to the hill and then walk around the path. So I need a geometrization of this network in order to compute the geodesics in terms of communicability distance that exists in this particular network. And we do this through the geometrization process of the graph. So we simply consider that every edge here is a compact one-dimensional manifold with a boundary given by the union of the two corresponding vertices. And then we weight every of these edges by the length, by the distance between the corresponding two nodes. But remember that this communicability distance between these two nodes take into account the influence of the whole network and the communication between the pair of nodes which are connected. So we can extend this to the whole network, and in this way, what we can have is the geodesics that goes from one vertex to the other. Let me put one example here. So we have the path P1 in the initial example and the path P2 in the second and the same example. And that what we have to do is to take the sum of the communicability distance of these three edges for the path P1 or these four edges for the path P2. So this will give you the length of the path in terms of communicabilities. So we can do this, of course, we already have the topological distance for the electric resistance distance. But then neither of these two cases tell us that the path P2 is less resistive than the path P1, as we have observed in the computational experiments that we have done. But for the particular case of the communicability path, we obtain that the path P2 is shorter than the path P1 in terms of the global resistance that the network offers to the communication between these two pairs of nodes. So you can immediately figure out what is happening here is that if you go from P to the nearest neighbor here, suppose that you are a random walker, but it's not totally drunk. So you try to remember that you have come over here. Then maybe you are not returning, but you have 1/3 probability of going to any of these three vertices. So maybe you end up here, you are not returning, but you have 1/2 probability of going to any of these two vertices. You end up here, but you are not returning, but you have 1/2 probability of going to any of these two vertices. So you can end up here at your initial state, and you have not repeat any edge at all. However, in the other path, if you are not returning, you go ballistically from P to Q. So this means that this communicability shortest path is capturing the way in which diffusive particles are navigating these networks. So we can think about the brain, for instance, as system, a complex system in which diffusion is very important, but maybe we are not thinking about traffic in a city. Well, this was exactly my idea when I started this collaboration, and what it comes as a surprise, and this is a city in Isfahan in Iran, and we have here two randomly selected origin and destination in this city, and then we have experimentally measured the amount of traffic that occurs, and this is very important in terms of cars per hour in the morning, so when you have the rush hour at all the intersection points. And this is in red here, the shortest communicability path. So it's the path that offers less resistance in terms of communicability. And this is the shortest topological path, which means the least number of streets in this particular graph. And as you see here, the thickness of the path represents the traffic. So you can immediately figure out that there was more traffic between these two pairs of nodes by using the shortest communicability path than by using the shortest path. We selected about 10,000 randomly picked origin destination places in this city. We compared the shortest communicability with the shortest path, but also with the shortest length of the path in terms of how many meters do you have in every street which is in this path, or the diffusion distance, or even the resistance distance. And in all the cases, the average of all these cases is that there is significantly much more traffic through the communicability than through the rest of the path. And maybe you can think, well, possibly people in Isfahan are absolutely mad. They don't use GPS, they don't use maps, etc., etc. Well, we have done this for Anaheim, which is a city in California, Winnipeg, they are in Canada, Barcelona here in Spain, and Isfahan. And in all the cases, there were more traffic through the shortest communicability path than through the shortest path. So you can obtain the explanation, both mathematically and intuitively, about why this happens in this paper that we published in Nature Communication a few years ago. But now let's go to the main goal of this talk, and is that, okay, so I want to see whether real-world networks are doing something in terms of this shortest resistive path that guarantee a better way of communication between pairs of nodes. So by the definition, it is clear that the length of the shorter resistive path between a pair of nodes is smaller or equal than the length of the shortest path in terms of resistive communicability distance. So when this inequality is strict, let's call this shorter resistive path a bypass. So why a bypass? Because it is a way a little bit longer than the shortest path in terms of the number of edges of going from one node to the other, but avoiding the hubs of the network, because the hubs are those that will trap the particle, the walker, around it, and will not leave the particle to escape to the final destination. So this is more or less an intuition from what happened in certain biological systems. So for instance, in most of the organs, there are certain revascularization that allows that arteries can communicate to each other. And in case of blockade by cholesterol or any other problem, the flow of blood can go from one place to the other. So this inequality here is trivial. So if we take the first inequality that I show you and decompose it as the average of the shortest path length, shortest communicability path length in this path multiplied by the number of edges that we have here, these continue to be smaller than this. And we obtain this very simple bound, but it's very simple, but it's very useful. So what I am expressing is that the average, so the ratio of the average of shorter resistive path to the average resistive path in the shortest path is upper bounded by the length in terms of the number of edges of the shortest path respect to the length in terms of number of edges in the shorter resistive path. Immediately you will see why this is important, but let me show you an example. So in a real world network or in many graphs, from one pair of vertices P and Q, you have more than one shortest path. So then if you are using this expression here based on the shorter resistive path, the first thing that you have to do is to identify all shortest path between the two nodes. Once you have identified all of these shortest paths, you have to calculate the shortest, you have to calculate the length in terms of the communicability distance for all of these shortest resistive path. And there is only one shortest resistive path that you have to identify, but in this particular case, you will have to do the calculation for this shortest path in red and this one in magenta. See that these are the values of this ratio, and then if you do the calculation only using the shortest path, you have to do only one identification of a shortest path. Then you calculate this ratio, which doesn't depend on the length in terms of the resistive path, and what you obtain is this upper bound. So the worst case scenario that you have here. So see that this should be the least resistive of the two paths, because you only save here 25% of energy going through this P2 than going by P1. Here you save more, you save almost 43% of energy if you go by P2 than if you go by P3. But see that in any case, the least that you can save is 25%, and this is given by this expression here. So now you can put this for the whole network. You can calculate this difference for every single pair of vertices in the graph and take the average among all the pairs of vertices in the graph. And here you have the result. So for instance, for this simple example, you have that the length of the shortest path here, which is P1, is this value here. The length of the average length of the shorter resistive path. So this means the average length of every edge, or the resistance that every edge offers to the transmission of information through this path, is of course smaller than this one. Then you have that, well, in this particular case, you can save exactly about 30% of energy going through P2 than going by P1. But this worst case scenario tell you a little bit pessimistic, well, but you save 25% of this energy. So for us, it's much better taking into account that we are going to apply this to real world networks of very large number of nodes, to use this simpler expression than to use this. But of course, you can do the calculation and obtain this number for every single pair of vertices in the graph. So I will skip this. Well, no, I cannot skip this, sorry. So what happens, for instance, in the two models that we were thinking before? So in the Watt-Strogat model, what you have is that when you have the circular graph, you remove one of the edges connecting pairs of vertices, and then you rewire this edge to another pairs of nodes. So what you really are doing is diminishing the degree of this pair of vertices and increasing the degree, slightly increasing the degree of this vertex here. So but now the shortest path between V and W continues to be this one in magenta. But what you have done is also creating a potential bypass, which is now in green here, that skip this red node, which is now the potential hub of this particular network. This happened again in the Barabachi and Albert model. So every time that you add a vertex and connect it to the most connected nodes in the graph, you are creating potential bypasses that goes without passing the hubs of the corresponding vertex. And of course, this avoid that the information get lost or get trapped at these particular hubs. So in these processes of rewiring, what we are doing is increasing, or at least changing, the richness in walks, which are in these graphs. So we can then calculate this term here, which is just the total number of weighted walks from V to W, divided by the all weighted walks between every pair of vertices in the network. And we can apply the Shannon formula to obtain a sort of entropy, which gives you how much variation in terms of walks has occurred in this network after the rewiring or after the attachment of new vertices. This is very simply to normalize, and then we can have a measure between 0 and 1, which is this S hat here. So now let's go to focus on the Watt-Strogat model. So what I am doing is exactly what Watt-Strogat did, but instead of measuring the average path length and the average clustering coefficient, I am taking here in red the walk richness that changed with the rewiring probability, and this gain in energy that implies to go through the bypass than to go through the shortest path. The first thing is that, well, the walk richness increased with the rewiring, and this is intuitive because we start from a regular graph and we are now changing these edges. But the most interesting result is that this energy is non-monotonic for the Watt-Strogat rewiring, but there is a minimum independently of the mean degree that we have in the network that occurs for P equal to 0.15. So then it means that there is one specific region in the Watt-Strogat model in which the communication is much favored going by the bypass than going through the shortest path. And exactly the same happens in the Barabási-Albert model. Of course, here we have to plot against the average degree because there is no rewiring here, but we have this point here for each of these corresponding models that we call the good navigational point of the networks. So in brief, we have that both processes that we have studied create enough walk richness by the rewiring or the attachment of new nodes as for certain bypasses among the pairs of vertices emerge. And these bypasses avoid naturally the hubs of the network, allowing items navigating them to save energy in relation to what it will cost to navigate through the shortest path. But what happened in real world networks? Well, we have here the results for about 60 real world networks. I am illustrating just a few of them. And here is the value of negative epsilon. So it means the amount of energy which is gained by going through the shortest path than by going through the, by going through the shortest resistive path or bypasses than by going through the shortest path. So for the USA Western Power Grid, which is a planar graph, not very rich in structural terms, we don't gain very much by using the bypasses. In reality, there are very few bypasses there. And this network is not designed to take bypasses. Possibly is a problem of the network because we already experienced some blackouts in every of these systems. But at the other side of the spectrum, we find the brain functional coactivation network, which is a network representing 638 regions of the human brain and how they co-activate to each other in a resting state. We have done this also when the people are doing some particular task. But what is interesting here is that these networks are designed to perform operations in diffusive way. So remember that we have trillions of neurons that need to communicate with each other by sending neurotransmitter ions or molecules, which goes to the blood or water torrents in the brain to diffuse from one place to the other. So let me illustrate here what is happening in this network. This is more or less how the network looks like. And then here are one example of 14 source destination pairs that has been randomly selected. And this is the time that is saved by using the shorter resistive path in relation to going ballistically through the corresponding pairs of vertices. See that there are saving of up to 200, more than 200% of whatever is measuring here, let's say that energy, but in general, for most of the pairs of source destination that we have selected, there are certain gains in this communication. Now we can compare how close these real world networks are to these networks hypothetically in the good navigational point. So what we are doing is basically the following. So you take a real world network, let's say that this one has 4,000 nodes and 13,000 edges, and we create a Watt-Strogat model for this exactly the same number of vertices and the same number of edges. So we create a circular graph with this number of edges and number of edges on number of nodes and number of edges, and then we rewire for probabilities between 0 and 1, and we calculate the similarity of every of these snapshots of this network with the real world network in terms, for instance, of the spectrum of the adjacent symmetry. Then, for instance, for the collaboration network in quantum gravity, which is this network, what we observe is that there is a minimum in this dissimilarity in exactly about the good navigational point. So then it means that for this particular network, it is more similar to the Watt-Strogat model exactly at the good navigational point, like if this network has been designed to have these good navigation properties. Of course, this is not always the case. So this is the P star here for the previous network. The human brain connectome has a minimum, but is displaced a little bit far from 0.15. This is a Thesaurus network. And there are other networks in which there is no one minimum here, and they look more similar to the random graph that appears when the rewiring probability is equal to 1. So this is everything that I have. So my conclusion is that a network is said to be complex if it contains enough rich walkness or walk richness as for bypasses emerge as alternative best communication routes between pairs of vertices. Or in other words, it seems that bypasses seem to sustain complexity in these particular real-world networks. So thank you very much for your attention.